But when I was learning everything I could about the C programming language, I managed to come up with an arithmetic expression where the order of evaluation was unclear. The specification was ambiguous on the order of evaluation on this crazy expression that I'd come up with. It was the C language specification written by some really sharp people, and it's been iterated on. At this point, the spec was 15 years old, so it had been iterated on so many times, and yet somehow this weird corner case had slipped through. And then, well, I read the next version of the spec and they'd fixed it. So somebody had found it and fixed that particular hole in it. But even experts writing down specifications inadvertently leave mistakes in them. And your job as a software developer includes finding those things. So when your boss comes to you and says, hey, here's a quick 2-sentence description of this project that I want you to work on for the next 4 months, it's up to you to ask questions and take that 2-sentence description that is missing tons of information and get that filled out. Like, ask the right questions, talk to the right people, make sure that everybody's interests are represented. And then when you've understood the problem, then you can go make a plan for it. Breaking something idiot-proof requires only finding the right idiot. Another specification issue that I had, and this happened to me at work, was there was some kind of cryptographic secret that was going back and forth between the client and the server, and that cryptographic secret was a number. And the specification said, here's an example of the number. And in hexadecimal, which we'll talk about this week, it wrote out the example number. And I'm like, okay, so I'm gonna take binary data from the server and I'm gonna unpack it into this number, and we'll check and make sure that the secret is correct. And so I did that, but the person who read the spec, who wrote the server, thought that the number wasn't going to be passed as a number, it was going to be passed as a string with the number in it. And so that's what arrived over on my side, and it broke, of course. Neither of us were wrong. The spec was just ambiguous. And neither of us, the mistake we both made was we did not see that, and we didn't get clarification on it. Could have saved us an hour's worth of trouble, or 2 hours between two people trying to figure out what was going on. In our problem-solving framework that we use, we say, think like a villain. So when you're writing your code, think, okay, if an evil genius comes along and decides to pass in weird values to my function, what's going to happen? How's it going to break? And that gets you pretty far in terms of finding holes in specs. Anyway, so keep that in mind. Part of the project this week is figuring out all the material so that you know what to change where. That is an integral part of it. But what are we doing this whole week? Let me give some framing at the high level for the first part. This whole week, we are going to build an emulator. We're going to write a piece of software that pretends to be a CPU and acts like a CPU. So that's going to be the whole week project. And we're going to just work in one repo the whole week. Today, we're going to talk a bit about number bases. Do we start buying Raspberry Pis? Or if you want to, it's not a requirement, but if you want to buy a Raspberry Pi, it's a fun little computer. And there is a microcomputers channel here if you're interested in that. Anyhow, so today we're going to talk about number bases like hexadecimal and decimal and binary. And then tomorrow we're going to do some bitwise stuff like manipulating individual bits with bitwise expressions. And the next day we're going to add a stack to our CPU emulator, so we'll talk about how that works. And finally we'll add subroutine functionality to it. which is like functions. So we got to have this sort of week where we're going to slowly build this computer to the point where it is what we call Turing complete. That is, at the end of the week, the software you write will be able to compute any value for which there's an algorithm, assuming it fits in your memory. So by the end of the week, you will have written a program that can compute anything, which is kind of nuts if you think about it. You're going to write a program that runs programs. And it turns out it's surprisingly simple to make that happen. Simple in quotes, saying the devil is always in the details. And what we'll do during the week here in Guided Project is we will write a smaller, simpler virtual machine or emulator that shows the structure of the thing and how it works. And so the stuff we write in class isn't going to be the stuff that you're going to write for the project, but it will be similar in structure and in theme. I used to have a window open. Where is it? There it is. Are we going to go into the halting problem? No, I would love to. If you're interested, the halting problem is a really famous problem in computer science. Remember how I said that your computer will be able to solve anything for which there is an algorithm? There is no algorithm for the halting problem. There are a few problems that are not computable. And they're pretty fascinating. The halting problem is one of them. So look it up in Wikipedia if you're interested. And I can geek out for just a second. How many of you have seen The Imitation Game? That movie with Benedict Cumberbatch about Alan Turing, World War II, the code breakers, all that. So that dude is awesome. Not like the stuff from World War II, awesome in its own way, already awesome. But beyond that, he did incredible work. So he wrote this. He was one of the first people who determined that you could make a computer that could compute anything. You could make a general purpose computer. And today that seemed kind of quaint. Like, what do you mean? We're surrounded. Like, my phone's a general purpose computer. All these things are general purpose computers. But there was a time we didn't know if that was even possible. And Alan Turing proved that it was possible. He wrote a paper on it. And if you ever want to read the paper, I can't recommend this book highly enough, The Annotated Turing, because the paper is fairly impenetrable. But what Petzold does in this book is he goes through the paper like section by section and then writes a bunch of stuff out about what all this means. So you can actually get through it. It's a great book. If you want to super geek out on what computation is, do that. Not required for this week at all, but it is a great book. And then one more book. I'll share these links in the notepad afterwards. If you like the stuff that we did this week and you want to take that to the next level, there's this book right here, The Elements of Computing Systems by Nissan and Shakin. Probably mispronouncing those names. This does what we're doing this week, except on steroids. Great book. I'll post links to those in Notepad. All right. Share. Come on, Zoom. You're going to share my screen. All right, there we go. Interestingly, there was another guy named Alonzo Church who simultaneously, when Turing was working on his proof of general purpose computing, Church was working on his own, using a different approach. And Church built a certain type of mathematics to describe computation. And that mathematics is called the lambda calculus, which is our namesake. And then I think he published like a week before Turing or something. And Turing quickly hashed out a proof called the Church-Turing thesis that showed that the two models of computation were equivalent. And then Church's lambda calculus got changed slightly, but mostly used in functional languages like Lisp. Granted, it is based on lambda functions, which are from the lambda calculus. So yeah, all of it. All right. Let's take a quick peek at what we've got for your repo. So this is the computer architecture repo. Actually, before I do this, I'll share this, but before I do this, the main idea for this week is that we want to look at how the computer works at a very deep level. The deepest level that programmers ever touch. Like below that, it turns into physics and stuff, like electricity and semiconductors and material science, things like that. Programmers don't go there. That's the voodoo dungeon of computing. But programmers can write software at a very basic level. We call it the assembly language or the machine code level, where you're writing the simplest instructions that the computer can understand. And so what we're going to do to help us gain an understanding of what the CPU is doing low level is we're going to write a program that pretends to be a CPU, thus gaining an understanding of what the CPU does. There is a stretch goal for writing assembly if you want. So I'm not going to make you, but it's there. So I've already written a whole bunch of programs that your emulator can run. So you don't have to worry about the details of writing programs to run in your emulator. You just have to write the emulator that actually runs them. And they're all little individual simple instructions, and you're going to go through an instruction at a time and do whatever it says to do. And by the end of it, we'll have a machine that can do anything. This is one of those projects that sounds kind of impossible at the front. And I'm hoping that as the week goes on, you realize that it's not as bad as it originally sounds. It's sort of like, we don't have time to do this in CS, but a lot of you use Bash right now. If I ask you to write your own version of Bash, you're probably like, oh man, turns out that's actually not that bad to get the bare bones core of Bash written. It's only like 150 lines of code. So we're gonna do the same thing here. Sounds intimidating up front, but not too bad. All right, so there's some things here. I'm not gonna talk about these in a lot of detail because part of the project today is to go through this stuff on your own and see what's here. Figure out what you need to look at and what you don't need to look at. I don't expect you to read everything in detail up front. I expect you to more be discriminating about it. Like, okay, I know what I need to do for my first step because it's listed here and it's also listed in more detail in the README in this directory right here, which you will have found because you're going to go through and inventory everything to start. So you know what you need to do for the day, but figuring out where you need to look to get that stuff done is going to be a bit more work than normal. Notice there's a FAQ in here. Got a lot of stuff in there. If I were you, I would pop the FAQ open and I would skim the questions, but not necessarily read the answers. But get, like, in your brain, if you skim the questions, it might trigger later when you say, okay, hey, wait a second, I need to solve this problem. I remember I saw this in the FAQ somewhere. So use that as a resource. There's also this thing right here. This is the specification for the computer. We're going to be working on the LS8 CPU. which is the Lambda School 8-bit CPU. Not a real CPU, although Tom Tartt has a side project where he's thinking about building one with an FPGA. Stay tuned. Maybe someday there'll be a real life version of this thing. So there's a lot of stuff in here. It just launches right in. It's like a specification that you might find in the wild. Specs aren't meant to be easy reading. They're meant to be concise and unambiguous, period. So it's not really a tutorial on what to do. It's just exactly what to do to get this working. Now, the LS8 has a lot of stuff in it. It has a lot of instructions. You don't need to implement them all. I won't stop you. If you want to do the whole thing, great. But you only need to implement the instructions for that particular day to be able to run that program for the day. So I think the first day's program has 4 instructions in it. You just need to make sure you have all of those supported in your emulator, and you don't have to write everything else. I will give you one more hint here. Interrupts is a stretch goal. So anytime you see anything with interrupts in it in the spec, you can ignore that unless you're going for that stretch goal. But otherwise, this isn't something you can read in sequence really and just make sense of it. But do skim it just to see what's in here. And then trust that later context will give it more meaning. If you do want to write assembly on that stretch goal, pop into the ASM directory. If you don't, then you don't have to ever go in here. But this is where the source code is for all the LS8 programs. Remember, you're writing the emulator that is the LS8 that's going to run programs. These are those programs that run on your emulator. And they're little test programs. So like the first day's program is print8, which prints the number 8 on the screen. That's it. I said it was 4 instructions, but actually it's 3. I'd forgotten. But this is what assembly language looks like right here. So these are the instructions that your CPU will run. And some of the programs can get more complicated with like looping constructs and stuff like that. So this is assembly language. This is what people wrote software in before there were compilers way back in the day. And as you can tell, it's not particularly readable. In fact, it's pretty horrible looking, which is why we use higher level languages today. It's really error prone and difficult to write stuff in assembly language. It's far nicer to write it in some higher level language and then take another program to convert that high level language into assembly for us. We call that program a compiler. And the compiler takes care of all of it, right? You're like, I'm just gonna write functions and be happy and not need to think about all this juggling act of everything that's going on under the hood. I'll trust that the compiler will generate good code that runs on the CPU. So only need to peek in that directory if you're doing that stretch goal, or if you're curious, which I highly encourage. It is the code behind the code. Absolutely. If you think about it, the CPU is just a bunch of metal and semiconductors and plastic and insulators and stuff. So, and it doesn't move. It doesn't have any moving parts. So how does something that has all this moving, that it doesn't have any moving parts, how does it make anything happen? It doesn't know the C language. It doesn't know JavaScript. It doesn't know Python. It doesn't know Swift. It's far too simple of a machine for that. Even in its complexity, it has to be simple. All it could do are these simple little instructions that do one thing, and then go to the next one, and go to the next one. And it maintains a little bit of state so that one instruction can do something and then affect a subsequent instruction. But that's about it. And when you write the code for this, for your emulator, you're going to find that you're going to find that the code that emulates each particular instruction is actually pretty short, like usually 3 to 5 lines of code per instruction. And yet somehow, in reality, on a real CPU, we're able to take these simple instructions that don't really do much on their own. We're able to put them together into like massive video games. And everything else. It's kind of amazing. And sure, there are a whole bunch of fiddly little instructions the CPU has to execute, but it's executing billions of them per second. And so on our glacial human time scale, it seems like the computer's doing amazing amounts of crazy stuff, when in fact it's just doing amazing amounts of really simple stuff. Anyhow, so give this thing a read to start. I would totally expect each of you to spend between 1 and 2 hours doing nothing but inventorying what is here and understanding the problem that you're going to solve for the day. And when you get to work, it may be longer. When I first started working at Activision, my first task was to fix a simple bug, and I was allocated a week for this simple bug. It was actually only an hour for the simple bug, but it was a week for me to get familiar with the million-line code base and figure out where everything was and how the build system worked and everything else, just so I could get the point I could fix that one bug. Your first job's likely to be something like that. People love to give bug fixes as your first job, first task at work, because that's your chance to get familiar with how everything works. All right. Any questions about any of that? Your task for the week, CPUs in general. I mean, we're going to talk way more about it coming up, but how's your senioritis level? Senioritis, 9,000 plus. Kind of to be expected. It's a lot of work to form new neural pathways in your brain to learn this stuff. And for the past, how many months has it been? 6 months? You've been doing that like 24/7. 8 months. So you've been doing this a while, right? And it wears you down. It really does. So what you're doing isn't easy. It's the absolute, like, hiking the PCT of learning how to do programming. Pacific Crest Trail, if you're a backpacker. No small feat. When you get to work, it's going to get to be a lot easier in some ways, because you're not going to be learning new stuff every day. You might be tasked with doing something over the course of a week that you've done before. And you're like, yeah, I got this. I've already done this type of problem, so I can solve it. And in a lot of developers' experience, after a while, you start to have the opposite problem. Like, where are the challenges? Bring me the challenges. If work gets too dull, then it tends to lose developers' interest, because deep down, we like solving problems like this. So if that happens, remember, there's always HackerRank or other things. All the instructors run problems like this just to stay sharp. But I can understand senioritis at this point. So we'll try to take it kind of easy. All right, first things first, let's talk about this. Number bases. What has anybody heard about number bases, if anything? Maybe nothing. There's more than one. Only like the one though. Total number of available numbers available in a single character. Yeah. Or maybe I'd phrase that as available in a single digit. Whoa. The tribe with some base 2 numbering system. Binary numbers have a base of 2. We use base 10 because we have 10 fingers. Go with single radix. There we go. So, yeah, when we're talking about a number base, we're talking about how many values can be represented in a single digit. And so what we're used to in base 10, of course, 5, 6, 7, 8, 9. This is our one digit. This is what we got. We can represent 10 distinct values. So base 10 can represent 10 distinct values with a single digit. Base 2 can only represent 2 distinct values with a single digit. Base 16 can represent 16 different values with a single digit. Base 1 million can represent 1 million different values with a single digit. I don't know of any base 1 million numbering systems. Yeah, computers do use base 2. But base 2 is actually more verbose. That is, the lower the base, the more digits you have to write out to represent a single number. Because each digit has less information in the smaller base. So if each digit has less information, then you need more digits to encode the same amount of information. Like if I were to write in decimal, which is base 10, the number 33, and I wanted that in binary, that would be this in binary, I think. If I have that right. So the binary version is different than the decimal version. It's longer because we need more digits to represent the same value, because each binary digit can only represent 2 different values, whereas each decimal value can represent 10. Now, what's important, what's really, really important right here is that these 2 numbers are the same. I've just written them down in different bases. If you talk to somebody who only knew binary numbers and you pointed at a table that had 33 apples on it, they would say it has 10001 apples on it. And you would both be in agreement about how many apples there were. You're just writing it down in a different language, as it were. So these are the same numbers. Am I off by a 0, Joshua? Let's see. 1, 2, 4, 8, 16. I am off by a 0. Sorry. I totally miscounted. I thought it felt a little bit light. Other cultures have had different number bases. All kinds of bases. Base 16 has been used. Base 64, I think, has been used. Base 36. And we're used to, there are even holdovers in other bases in different, strange different places that exist. Like, until, I'm not even sure when the transition happened, Britain had a different number base for its currency, right? It had different values, different numbers of things that went into different sizes of currency. It wasn't a base 10 currency system like they use now, like we use. But there are other things that we think about without even trying that aren't based around 10. So Let's see here. Do you think the first computer architects had to go with base 10? If they had, there would be more widespread understanding of computers and programming. Maybe, but they had good reasons for not doing that. And I know there have been computers that have been created that were other bases. It's not impossible, but there are reasons. We'll talk about this in a little bit. Let's see here. Yeah, line 17 is the binary representation of the number 33. So this is the value 33 decimal. It's just written down in binary. This is the value 10001, except it's written down in decimal. These two numbers I have, exact same value, just a different, you can think of it like a different language for writing them down. All right, so base 10, we call this decimal. This is what we're used to. Base 2, binary. This is all you can represent, 0 or 1, that's it. And then another extremely common one is base 16, which is all called hex or hexadecimal. Which has 16 digits. Actually, I'm going to be lazy. We're just going to steal all our base 10 digits to start. But it's got 16 digits. So where do we go after 9? Hexadecimal, or hex for short. A through F. We need more digits. All right. This means that base 16 encodes more information per digit. You can represent the number 10 with just a single digit, right here, the letter A, or the number 15 with a single digit, the letter F. This means that hexadecimal numbers tend to be shorter when you write them down than decimal numbers because they encode more information per digit. Now, with hexadecimal, programmers, when they're writing out binary values, they don't actually tend to like to write them in binary. They tend to like to write them down in hex. They convert them to hex instead. So instead of writing this number in binary, we could do 21 in hex, I think. Did I do that right? Or am I off by one again? No, I think that's right. We'll talk more about how to do that in a second. Somebody can correct me if I'm wrong. You can also always Google, what is this number in hex? And Google will tell you. But why? Why would programmers prefer to write things in hex instead of binary? It sure is less writing. Man, is it less writing. And it turns out that due to it's not actually a coincidence at all, due to a deliberate planning, it's really easy to convert between base 2 and base 16 because 2 and 16 are both powers of 2. It makes the conversion simple. So developers who work at this low level, they're able to take a hex number like this and quickly in their heads see what it looks like in binary. It's how R2B is represented. Yeah. From those of you who are coming from the web side of things, or even, I don't know, maybe they do something similar in iOS, you've definitely seen some CSS that looks like this, right? Or something. And red, green, blue. What color is this? Is this cyan or something? I can't remember which color this is. But this is actually a triplet of hex numbers. FF and 00 and FF. And FF in hexadecimal is equivalent to 255 in decimal. We'll talk about why that's important in a little bit. Put an alpha channel out there. Does that actually work? You can put like a quad in CSS after the hash mark. In my brain, that doesn't work, but oh, that's awesome, because I always use the RGBA thing. Learn something new every day. All right. So let's do some of these conversions and see how this works. And we should also talk about how multiple digits actually work, multiple places in a numbering system. So I'm going to take this thing. Do I have focus? Focus, not on you, but on you. Where am I typing? Am I off the bottom of the window? Is that what's going on here? Yes. All right. So here's a quick, dirty little diagram. This is what we know from grade school, that when you write down a number in decimal, like 1, 2, 3, 4, that this is the ones place, this is the tens place, this is the hundreds place, and this is the thousands place. So by now, this is second nature for you. But let's stop and just break it down a little bit lower level so we can see how it works with other bases, because it works exactly the same in other bases. You just count at different intervals. So what happens when we're counting up in decimal? Well, let's start at 7. I'm just going to count up, right? 7, 8, 9. I'm out of digits. I've run out of digits. And this problem happens in every number base. Eventually run out of digits. And so what we've decided to do mathematically, and this is just something that people decided worked well, we've decided that, okay, we're going to, since we've run out of digits in our ones place, we're going to make room. And we're going to put another digit here that represents the number of tens we have. And so I've got up through 9, and now I'm going to say I have 1 10, and then I'm going to put how many ones I have. 1 10 and 0 ones. And we add all these things together. 1 10 and 0 ones. And then we go to the next one, we say we have 1 10 and 1 1, and then 1 10 and 2 ones. And we add those together to get the actual value. And so we've just decided that we need another placeholder out here to represent the next number up in the base. And of course, we could put leading zeros on the front of that if we wanted. That doesn't make any difference. I'm doing this here because we're going to do it a lot in binary. We're going to throw leading zeros on. They don't matter. Because why don't they matter? I'm saying I have 0 tens and 7 ones. And 0 tens plus 7 ones is 7. And of course, after a while, we get up to 99. And now I'm out of digits again. I've like rolled both digits up to their maximum. I can't put anything else in here in 2 digits of space. I need something to represent the number 100. And so we do the same thing again, give ourselves some room, and we say we have 1 100, 0 tens, and 0 ones. How many of you have thought about this at this level before? It's kind of funny because when I was learning this, I was like, this is what I've been doing the whole time. I just never thought about it. It just came like, because I've been doing it for so long, it was just second nature. And hadn't thought about it at all. So in a second, we're going to switch bases. We're going to do the exact same thing because all number bases work the same. Christian, it is crazy. Like, how did we do anything before 0? Just so weird. All right, so let's switch bases. I'm gonna switch to binary. I'm gonna paste this down here. Base 2 is binary. I'm gonna write some binary number in here. Let's make it that number. Be interesting. Let's see, 1, 2, 4, 8, 9. Yes, this is 9 decimal. 1001 binary is equivalent to 9 decimal. So check this out. If this is decimal, how can this be the ones place, and how can this be the tens place and the hundreds place? Or if this is binary, rather. What kind of sense does that make? If it's binary, it's got to be different, right? But here what I've done is I've written all these numbers in binary. So this isn't 10 decimal, this is 10 binary. This isn't 100 decimal, this is 100 binary. Turns out the same thing happens when we're counting up in binary. So if I start counting up in binary, I go 0, that's the first digit, then 1, and now I'm out of digits. Just like happened in base 10, I'm out of digits. So I need to scoot things over to make room. And now I say I have 1 of these and 0 of these, and then 1 of these and 1 of these, and now I'm out of digits again. So got to scoot it over to make room. And then I have 1 of these and 0 of those and 0 of those, and so on, until I run out of digits again, and then I have to scoot everything over. So when we're talking about stuff in binary, and this gets a little bit confusing, we often refer to the places in decimal. So in binary, I would say this is the ones place, this is the 10's place, this is the 100's place. But when we're talking about it, like I said, commonly we say we put this in decimal. The 1's place, same. This is the 2's place, and this is the 4's place, and this is the 8's place. So this number right here is written in binary. This is the decimal equivalent. So 1000 binary is the same as 8 in decimal. And now that we've written these in decimal, we can actually do some math to figure out what this value is. Isn't it a trip that the places are still written the same when you write them down in binary? If you stop and ponder this for a while, you'll realize that they have to be, because this number represents the value when you first run out of digits, just like 10 represents the value up here when you first run out of digits. You've got 9 digits, so this one must represent the value 10 because you've just rolled over. Alexander, each time you move it over, you have exponentially greater options for values associated with the binary. So you're looking at the fact that we had this, we scooted it over, then we had 2 of them here, and then we have 4 of them here. And if we scoot it over again, we're going to have 8 of them here. Right? So we got 8 of them with 4 digits. Yeah. So each time you scoot it over, you have exponentially greater options for values being stored with that number. But that's exactly the same as with base 10, too. Every time you give yourself another one of these things, you get 10 times the different values. Every time you add 1 additional digit to base 10 number, you get 10 times the number of values you can represent. So with a 2-digit base number, you can represent 100 base 10 numbers. You can represent 100 values. With a 3-digit base 10 number, you can represent 1,000 values. Yeah, so the number of distinct, I'm spelling distinct values by a base B number of D digits is, so base B number of D digits, it's B to the D power, B raised to the D. So with 4 binary digits, we can represent 16 distinct values, because 2 to the 4th is 16. With 4 decimal digits, we can represent, if I can do this right, 10,000, because 10 to the 4th is 10,000. Is that right? Well, let's do this conversion really fast here on this number, 1001. I've got, one way of writing this is I have 18, 0 4s, 0 2s, and 1 1. I've got 1 8 because this is the 8th place right here. And I've got 0 4s because this is the 4's place, 0 2s because that's the 2's place, and 1 1. So what is the decimal value of this number? If I wrote this mathematically, I'd say I have 1 times 8, 0 times 4, oops, plus 0 times 4, plus 0 times 2, because I have 0 2's, plus 1 times 1, because I have 1 1. So what's that add up to? 9. That's it. Okay, so this value binary is equivalent to 9 decimal. And we did that just by adding up those places. If we wanted to do the reverse, if I wanted to give you some decimal number, like 234, is equal to what in binary? To be honest, I would Google. But what we really have to do is figure out how many of these different numbers add up to this thing. And so we've stopped at 8 here, but we really have also the 16's place. And I'm going to make more up here, 32, 64, and 128th place. So those are all farther out to the left. Notice all I'm doing is doubling the number. It's 2 to the 0 is 1, 2 squared is 2, 2 to the 1 is 2, 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16. I'm just adding or multiplying another 2 onto each of these. Just like up here, we multiply another 10 on to each of these to get to the next place. This is base 2, so we multiply another 2 on. So the trick is when going this direction, we got to figure out what collection of these numbers we can add together to get that number. So we can add 128 and 64 and 16 and something and something. There's some combination of these that we can add together to get 234. And I don't know what it is off the top of my head. All right, so apparently the combination is 128 plus 64 plus 32 plus 8 plus 2. Is that right? I always start at the highest value, and then I start subtracting away, right? So I'll take 2 of 34. I'm like, well, clearly 128 fits in 234. So let's get that out of there. And then I compute 234 minus 128, whatever that is. And then I see that 64 fits in that result. So I add one of those. Basically, you're going to grab the highest possible number you can. The one that's after the 128th place, incidentally, is the 256th place. So this number is too big. 234 has 0 256s in it because 256 is bigger than 234. And so if we know if it has 128 and 164, we can start writing this down in binary. 128, 64, 32, but there's no 16. So I leave that off, 0 16s, but I've got 1 8, so 1 8, 0 4s, 1 2, and 0 1s. So I end up with the binary representation of that number. This is the most difficult conversion for me, going from decimal to binary. So again, for these, you can always Google the answers, but I've always found that having a deeper understanding of how this stuff works makes it easier to see things that are wrong. Like if you're writing some code and you're like, hey, wait a minute, that hexadecimal number is not right, because you're used to doing the conversions in your head. And it can just make your life easier anytime you run across any of them. So you'll have plenty of time to give this practice if you want to. You can, we're going to be doing a lot of binary stuff this week. So you'll have opportunities to convert that from binary to hex or to decimal as you want. And of course, there's ways to do it in software. Like whatever programming language you use, there's going to be a way to convert a string that is binary to a string that is the hex or something. All right. Before we take a break, I want to stress something about numbers and how they work inside the computer and how they relate to variables that you use in your programs. This is an important distinction to keep in your head. The number base only matters when you write the number down somewhere. That's when it matters. When you're doing math on numbers, it doesn't matter anymore. So once you have values and variables that you're doing math on, you can just think of those as pure numeric values. There's no base associated with the pure numeric value, just like there's no base associated with the number of apples on your table. There's just a pure numeric number of apples there. It's only when somebody decides to write it down or decides to say it out loud that suddenly it matters what the base is. And so when you write something down in code, it matters. When the user inputs something as a string and you need to convert that to a value, the base matters. Did the user just enter the number 100 decimal, or did they just enter the number 4 binary? They need to specify. The base matters when you write it down. But again, once it's inside the machine and we're doing math on it, then as a programmer, you can stop thinking about it as being a particular base and just start thinking about it as being a numeric value. Now, of course, deep down, it's probably stored in binary with like electricity and capacitors and stuff. But from a programmer standpoint, variables just have values in them, no base. It's only when you print it out that the base matters. And so we do have to be careful when we're coding to specify the base. If I write this line of code right here, what did I just write? Is that 10,000? Is that a binary number? The Python, your programming language, isn't going to know unless you tell it specifically. Now, by default, Python assumes you meant base 10. But if you wanted to make it binary, you've got to put a 0b in front of it to indicate that this is a binary number. I'm writing it down in my code, so base matters. If it's hex, then we got to tell it that too, by writing 0x in front of it to indicate this is a hex value. So again, we're writing the number down. We got to be clear on the base. That also happens when we do conversions. If we have a string that the user's inputted and they've typed in the number 1000, and we want to convert that string into a number, we have to specify a base for that thing. See if I can remember how to do this off the top of my head. So if I have a string like this, and we want to get a value out of it, we can convert that with int into a value. And it's like, great, that's 1,000. But what if that string were base 2? We'd have to specify a base. And you can do that. Here I'm saying, hey, that's actually a base 2 string, so convert that into a value for me. And then Python's going to print that out as a decimal number. So this is why in some programming language you have to specify it's a long int or float, like in the C programming language. That's not so much a base thing as a size of variable, like long int versus int, like how many bits of storage for that particular variable. On the LS8, we're only going to use 8 bits of storage for all of them. So there's no such thing as a long int. We don't have any floats either. Bases are a stylistic decision. Why doesn't everybody just standardize and use the same base? And that's a great question. And the answer is that sometimes your code is clearer if you write it in one base or another. So you should use the base that makes the most sense. Now, when programmers are thinking about individual bits in a number, they tend to use base 2 or base 16 to write that down. And when they're thinking about some human value, like the number of apples on the table, we tend to use base 10 to write it down, because that just makes the code clearer. So let code clarity be your guide. You're dealing with like low-level networking stuff, lots of individual bits going by, lots of hex. Speaking of binary, it's 10:10 a.m. or 2 a.m., I guess, if we use binary clocks. Should definitely take a break. So let's do that. And when we come back, we will do some programming. Come up with a little virtual machine. It's binary times all over the place. All right. So I always used to do the rooster, but lately I've been having people choose different ones. What are we looking for this time? What's your favorite alarm out of all this stuff? No idea what this is, but that was first, so that's what it's going to be. All right, everybody grab your coffee and we'll catch you in 10. That was very calming. All right, is everybody coffeeed up? All right. Before I go into coding a little bit here, I want to show you one more thing about conversions that is really useful for binary and hex. This is the trick for converting between binary and hex. So let's run this for a second. I can give you arbitrary binary numbers, like this crazy thing. And it's actually pretty easy to convert this to hex. And it's all because of the nice, happy fact that both hex and binary have powers of 2 as their basis. So the trick is split the number into nibbles, sometimes spelled with a Y, which is 4 bits. A byte is 8 bits. A nibble is 4 bits. It's silly, but it is. So first step, we're going to take that number right there. I'm going to split it up into 4-bit chunks. Actually, I better start from this end because I'm not sure if I have an even number of 4 bits here. So I just made that up. And we don't. I'm going to put a leading 0 on there just so we have 4 bits. You can always put a leading 0 on a number. And then we're going to convert each of these in isolation into hexadecimal. Each hexadecimal digit can represent 16 different values, which, not coincidentally, is the same number of values you can represent with 4 binary numbers. So 4 binary numbers is the same as 1 hexadecimal digit, which is why we split it up into 4s like this, because each of these represents 1 hexadecimal digit. We just have to do that conversion. And usually I do that by converting it to decimal. And if it's more than 10 or more than 9, I count on my fingers how many letters it is, except for the few that I have memorized. So I'm going to convert this number right here to decimal. And I see that I have 1 1, 0 2s, where am I highlighting? 0 2s, and 1 4. Somebody tell me if I get any of this wrong. I've got 1 1, 0 2s, and 1 4. So 4 plus 1, that's 5. That's this digit right here. So I go to the next one. 1 0 1 0. I've got 1 8 and 1 2. So 8 plus 2 is 10. But 10 in hex, I have to do a conversion. Now I have to think about it. And 10 in hex is A because it goes 7, 8, 9, A to represent 10. And this is one of the ones I have memorized. Because 10, 10 in binary, I've just memorized that that's 10 in decimal. Because it kind of lines up that way visually, right? Just a coincidence. And I've also memorized that 10 decimal is A in hex. All right. So here we've got another 1010, which is 10 decimal, or A in hex. And here I've got, what number is this? Converting this to hexadecimal. Nine. I've got 1 1, 0 2s, 0 4s, and 1 8. 1 8 plus 1 1 is 1 9. There we go. And then we'll keep going. This one gets a little bit trickier. This is 11, which must be B. If A is 10, 11 must be B. 10, 10, we've seen that before. That's A. What about this one? Another one I have memorized. All ones. Yeah, all ones is 15 in decimal, which is the highest single digit in hex. Because hex has 16 different values. They go from 0 to 15. So F is that value. So I always remember that a string of ones, that's an F. And then 10, 11, we saw that before. That was B. And there we go. Then we take all those numbers and we cram them back together again. And that's a hex number right there. Put a 0x in front of it just to let you know that it's hex. But this hex number right there represents this binary number right here. So that conversion is pretty straightforward. Now converting this to decimal, that's a different story, because now I'm adding like 1 plus 2 plus 8 plus 16 plus 32 plus, it's not a straightforward conversion into decimal. That's where I'd Google. But it's kind of neat that 4 decimal or 4 binary digits represent exactly 1 hex digit, and vice versa. You could easily go the other way by taking this number, splitting that up into individual digits, and converting each of those digits into binary, and then putting it back together. So kind of a neat thing there. So I'm not expecting anybody to be a number-based expert at this stuff at this point, but do think about it when you're working with the code this week and practice it a bit. And we're also going to learn how Python does this stuff, converting strings into values that you can use to do math on. Oops. And also the other way around. I don't know. What does everybody think about our quick foray into number bases? Huh. This is going to come into play mostly this week because the programs that your program is going to run are written down in binary. So we're going to have to do some parsing to take those binary strings that are in a file, convert them into values so that you can operate on them. But that's pretty straightforward in Python, as we just saw right there. You can just use the int function and give it a base, and it'll do the conversion. Incidentally, if you try to do the conversion in Python on something that doesn't make any sense, like for instance, if I have a hexadecimal string, like A4B, so there's my hexadecimal number, and I try to do a conversion on it at base 10, which is the default, it will puke on it. Invalid literal for int with base 10. It's like A, it's looking at A, it's saying A is no digit I've ever heard of base 10. So no. But if I tell it base 16, it's like, sure, I can do that. I know what A is in base 16. If we have time at the end of the hour, we'll jump into base 64 for a second. Kind of a neat thing. But if you think about it, base 64 has got to have 64 different digits. What could they all be? Anyway. Yeah, actually, that's one of the reasons it's made, so that it can be terse. All right. Well, if you have any questions about number conversions or that whole idea, that really important idea that once you have the number stored in a variable, it just kind of exists in a pure mathematic sense and not with a base associated with it. It's only when you write it down that the base matters. And by write it down, I mean the user types it in, or you write it in your code, or you print it out on the screen. That's when the base matters. Keep those questions coming about that. In the meantime, I would like to code up a little CPU, just a tiny one that does a couple things. And this is not the LS8. This is not what you're going to be coding this afternoon, but it's very similar in structure to how you're going to be coding it. And it's definitely the same in concept. So this will be an example. Yeah, if the base is really high, you just keep using ASCII characters. So base 64 needs 64 digits. We've got 26 uppercase, 26 lowercase. That's 52. That's not 64. We need some more. So we can use 0 through 9. That's 62. That's still not 64. So we need some more. So they added a couple extra characters. I can't remember what they are, plus and slash or something. True. All right. So I'm going to write a program that runs programs. And I'm only going to have one set of instructions for this, or one instruction to start. Now it's going to be two, actually. I'm going to make an instruction called print Beej. So this is my program right here. Print Beej, halt. So this should print Beej twice and then stop. That's my program. So now I'm going to write a piece of software that will actually run that. So how can we make this happen? First of all, I'm not going to use strings like print Beej and halt. I'm going to actually make those numeric values, because deep down in the computer, we've got a bunch of wires, and each wire has voltage or no voltage on it. Voltage might represent a 1, no voltage represents 0. That's all we've got. The computer doesn't know what a letter is. All it knows is numbers. Deep down, all it knows is voltages on wires. But really, all it knows from our perspective is numbers. So I'm going to make up numbers that represent these things. So I'm going to say print Beej is 1 and halt is 2. And then I'm going to take these instructions and I'm going to store them somewhere so that I can execute them. I'm going to put them into memory. Like this. So now I've got numeric values associated with the instructions, and I'm just writing them here as the variables so that we can read it more easily. I could have written 1, 1, 2 right here, but that doesn't read at all. So we're going to keep it like this for now. All right. So if I want to write a piece of software right now that goes through this memory and prints Beej twice and stops, what kind of plan can we come up with? Is there anything in the understanding phase we're still trying to think about here? I want to write a piece of software that goes through this memory array and does whatever the memory array is saying to do, and when it gets a halt instruction, it quits. Any more questions about what I want to do and ideas for how we could make it happen? Remember, your job as a software developer is to find holes in the spec and ask questions about them until it is clear. While current is not equal to, print the current index. Might be helpful to have some regex. Since our commands like print out the text. So for print Beej, all I want to do is print the word Beej on the screen. That's it. So nothing too complicated at this point. But yeah, some kind of thing. Well, we're not halted. We keep track of the current index of where we are. So maybe this is like the current index in the array where we're at, okay? And then while memory at the current index is not equal to halt, oops, halt, I'm gonna use that symbolic name I defined up here just to keep, I wanna keep magic numbers out of my code as much as possible. Then we need to do something. What do y'all think? What should we do from here? We're not gonna go that low level, Jack, for this. That book that I had, that I'll post a link to, computing, whatever it was, Elements of Computing Systems. That one goes to that level. Yeah, we could use some hash map. That is actually part of your goal, is to use a hash map. I'm just going to use an if-else cascade right here because it's a little bit cleaner to reason about. But I could do something like this. If memory current index is equal to print Beej, let's do that. Yep. And we absolutely do. Jack, we're writing like an emulator here, but we can take full advantage of anything Python has to offer. So we don't have to go to the level of emulating like how a screen bitmap works or anything like that. I mean, you could if you wanted to. That would be a great stretch goal, but we don't do it this week. So like inside the LS8, there are two instructions, one for printing a number and one for printing a letter. You could just use print to print those. That's it. What am I missing out of this thing? Yeah, I'm missing incrementing the counter. Yeah, I might clean this code up a little bit. So let's implement the current. Let's increment the current index first. Oops. So let's go to the next one, and then instead of putting this in here, I might make a thing like this. Halted is false, and then I might grab this and throw it down here, and then while not halted, let's do this, and then I can do else if memory current index is equal to halt, then we can halt. All right. Just cleaning it up just a little bit here so that we're checking individual instructions. If it's print Beej, do this. If it's halt, do this. And then I'm going to add a catch-all, which I highly recommend you all do because it'll make debugging a lot easier. And I'm going to print out an instruction. And then I guess we might as well just quit. I'll bail out of the program. Oops, sys All right. I've repeated myself in the code a little bit here with memory current index. I'm going to actually pull this out. Instruction equals memory current index. So in memory, at the current index, we'll pull the instruction out, and then we'll do something based on it. Let me replace those down here. All right. I could use a for loop and then break out of it, but since I had a true-false condition for whether or not I wanted to loop, I felt more like using a while since it uses a conditional like that. But really, any type of loop that gets it done is okay. So if this works right, we're not halted, the current index is 0, we get the instruction from index 0. If it's equal to print Beej, which it is, we print Beej, and then we go to the next one. And then we do it again, and then we get to this one, the halt instruction, which we hit right here. We say halted is true, we move the index up, we bail out of the loop, and we're done. Let's give it a try. Hey. Now in theory, if I go up here and I get rid of one of these, I change my program. Should only print Beej once. And if I had a bunch of them, it should do it a bunch. This is the core for what the emulator looks like. We go into memory, we grab an instruction out, we decide what to do, and the LS8 spec will tell you exactly what to do with that instruction. And then we execute it. Today, it's going to ask you to print out a number with a PRN instruction, and you can use print to make that happen. I'm going to change one more thing here. Current index. This is which index in the array that we are currently executing the instruction for. Inside the LS8, current index is called the program counter. This is also a pointer. It's a currently executing instruction. So I'm going to use PC here as the current instruction, just because that's what the LS8 does as well. All right. How do we feel so far on this? This is the core. This is the core of all of it. Pretty simple loop. Some of the instructions get more complicated, but none of them get super complicated, not until you get to interrupts anyway. Make the window a little bigger. These up here are just so that I don't have to write those numbers in here. Like if I really wanted to, I could have changed all these to this. But for me as a human, I have a lot of trouble reading what that does. And as a general rule, when you're coding up something with numbers that have a specific meaning like that, it's a good idea to give them a symbolic name, something humans can read, so that programmers that have to read your code don't hate you. Does that make sense, Joshua? And Alexander, it's definitely abstracted for sure. We are going up a level, right? We're going meta. We've been writing programs this whole time. Now we're going to write a program that runs programs. Does it get more complex if memory is a graph or something? No. Well, no, with an asterisk. Memory is, in almost all CPUs I'm aware of, memory is a linear stretch of numbers. You can think of memory as an array. End of story. And deep down, there are things like virtual memory where the CPU is juggling stuff behind the scenes. But from the program's perspective, memory is a big array. It's got an index, and it's got value at that index. It's just a big array. Hold that thought, Jack, because I want to implement one more thing here before we and then I'll, because right now there's not enough here for it to really relate to a computer. But let's do one more thing today, and then there'll be something there to relate. Well, I'm using the numbers. I'm using the numbers all over the place. Like print Beej, I'm using this variable. It's just a variable, right? So I'm using it here and here and here and here. All I've done is give it a name, print Beej, so that we didn't have to write the number 1 all over the place. So they are being used. So I want to do something different with this machine now. So print Beej isn't very powerful, but let's do something different so we can relate it to how a real CPU works. I want to store numbers in variables effectively now. So not only do I want to be able to print Beej, but I want to be able to store a number in a variable, and I want to be able to print out the number that's in that variable. So I want to change this machine from being a simple thing that just does one instruction after another to being something that can do one instruction after another. But some of those instructions are like assignments. Store a value in a variable, print that value out. And to do this, we're going to use something called registers. And this is going to be an array, and I'm just going to make it an array of 8 zeros to start. So this is an array of 8 zeros, a list of 8 zeros. These are going to be our variables. CPU parlance, they're called registers. You have a fixed number of them, and they have fixed names, like R0, R1, R2, up to R7. So they're like variables, but we're kind of restricted. We've only got 8 of them. You could store things in them. You can print those things out in it. This is our goal. So I want to be able to write a program that prints Beej out and then saves a value in a register. I want to save like the value 10 in register 2, say. Remember, we've got 8 registers. They're all named R0, R1, R2. So we'll just use R2. I want to save that, and then I want to print the register value out. That's in register R2. And that. So this should print Beej out. This should save 10 in register R2. And then this should print it out. This should print out the number 10. If I were writing this code in Python, I would write this, and then I would write this, and then I would write this, and then we'd quit. So this is the Python version of the code I've written right here. Ish. Lines 8 and 9 aren't valid Python. We'll fix that in a second. But does everybody see how that code that I have highlighted is equivalent to this code down here? How do we get the reference to the register? Yeah, lines 8 and 9 are clearly broken, because that's not good. Python's going to hate that. How do we refer to these things? Now remember that inside the CPU, everything's numbers. There's no such thing as the letter R. So we have to refer to these things by number. And the way this typically works is that we'll put save reg, which I better make an instruction here. Save reg, I'll just keep going up, call that number 3. I'm choosing these numbers arbitrarily. I just need unique, distinct values to represent the instructions so that we can switch on them down here in the if statements. So save reg will be 3, and then we put the arguments afterwards. So the next thing in memory might be 10, and then I need something to represent register 2. What would be a good number to represent register 2? Because everything has to be a number. Save reg is 3. We want to save 10 in register 2, but I need a number that represents register 2. Any ideas what a good number would be for that? 4 could work, or I could use 2 to represent register 2 and 0 to represent register 0. But 4, I see where you're going because we've used 1 through 3 up here, right? So in your thinking, this space where we're putting these numbers, these are instructions. But anything after that that are arguments, these are kind of different spaces. So I could use 2 here to represent register 2. This is the value 10. And this is the instruction 3, right? Because save reg is 3. So, but what about the 2 halting? Wouldn't the 2 halt? Because this is a great question. I've got 2 here for register 2, but 2 is clearly a halt instruction. Now what am I doing? And how can that work at all? I mean, if we start using all these numbers for these things, how can we use those numbers for other things, like the value 10? How are we allowed to do that? So Jack's onto something here. We need to do things a little bit differently when we find instructions that have arguments to them. Arguments are also called operands in assembly language. So this instruction I have highlighted is actually 3 elements big in the list. This instruction's 1 element big. This instruction's 1 element big, but this one's 3 elements big. It's kind of a special case. And it turns out in the LS8 we have lots of instructions that are 1 byte, lots of instructions that are 2 bytes, lots of instructions that are 3 bytes. So in our handler code, we've got to take that into account down here when we move the program counter up to the next index. Program counter should always point at an instruction, and it should never point at data like this. The data that I have highlighted here, these arguments, program counter should never point here. And if it does, accidentally, like you have a bug in your program, and the program counter ends up right here on this number represents the register 2. But if the program counter is on a 2, it halts. The CPU will just blindly do whatever it lands on. So if you have a string in the middle of memory that says hello world, and you throw the program counter in the middle of that string, the CPU is going to try to execute it as instructions. So it's up to us to make sure that the program counter never ends up on data like this. I'm going to write this out. Save reg 10 in R2. Say reg value 10 in register 2. Just so we're clear that this is what the instruction is doing here. But could you have any number of arguments to save reg? No. You can only have 2, period. Inside the LS8, save reg is called LDI. This is the LS8's version of save reg, and it tells you inside the spec exactly what it takes. No more, no less. The spec is exact. It takes a register and it takes a value, end of story. So we know that LDI is a 3-byte instruction. And for every single instruction, it's all in the spec. We know how many bytes the instruction is. It's listed out here in binary with a couple fillers that are described earlier in the specification of what these mean. Or you could just look up here and know that every argument is 1 byte long. So we know that this is a 3-byte instruction. 1 for mul, 1 for the first register, 1 for the second register, and so on. And here's a 1-byte instruction, 1 for no op, that's it. So everyone has a fixed number of sizes. Now for print reg, we should do the same thing that we just did. Print reg should be 4, just going to the next instruction. Print reg into register 2. Or print reg register 2. So we want the value that's in it. So I'll just put 2 there to represent register 2. All right. So now we just got to code it up. So this pattern gets to be common, where you're like, okay, next instruction, let's go add a few lines and make it happen. Else if instruction is save reg, I need to get 2 pieces of information about this instruction to help me out. I need to get the value, and I need to get the register number to save it in. This is the part that starts breaking brains. So I know that the PC is right here at this index. So yeah, the value right after the PC has to be at index PC plus 1. And the next one has to be at index PC plus 2. So I should be able to fetch those straight out of memory. So PC is where the instruction is. PC plus 1 was where that value is. And then PC plus 2 is the register number. And now I can do that work. I want to store this value in that register number. And I have an array right here of registers, a list of registers to store it in. So I've got a register number, which is the index into this list, and I've got a value to store there. So let's store it. At this index, store this value. Yeah, so this is broken because we're only moving the PC up 1 per instruction, but that's not true anymore. We should move it 1 for this guy. So for this one, we have to move it 3 from here, 1, 2, 3, down to here to get to the next instruction. Remember, we want the PC to always point at an instruction, not at any of the arguments to that instruction. So I'm going to fix that up. So for print Beej, that's a 1-byte instruction. I'm going to add 1. Save reg, that's a 3-byte instruction. I'm going to add 3. Print reg, that's a 2-byte instruction. I'm going to add 2. So let's move this thing up here. 1-byte instructions get 1 added to them, like those. 3-byte instructions, I better do it at the end actually. 3-byte instructions get 3 added to them, like that. Okay. So now when we get save reg, we'll grab those first 2 values out, the value, the register number, and then we'll move the PC all the way to the next instruction. Let's try it. All right. You'll have a while loop like this. You're just gonna, by default, the instructions will push the PC down to the next one. So you're still gonna wanna have a while loop while you're not halted, while the thing is running. I've blown it here though, because I've got unknown instruction at index 4, which is right here, right? Index 0, 1, 2, 3, 4. Index 4, print reg. I just simply have not handled that yet. So my unknown instruction thing let me know, hey, there's an instruction here you're not handling right. Great. So let's just do that in a big hurry. For print reg, I need to get the register number, which is in memory right after the PC. So I'll grab that register number directly after the PC. One more, the next index down. And then I just want to print that out. Print out the value in that register. And this is a 2-byte instruction, so we add 2 to go to the next one. So let's give that a try. See if we get our value printed out. And there it is. Give myself another window here. So if I go to the top of my code, I should be able to change this code out. I should be able to save the value 20 in register 2 and then print it out. So that should print out 20 or whatever. I could change the register number to register 3 and print that out. Still works. Or I could have a bug in my program where I saved it to register 2 but printed out register 3 instead, which is just going to print 0 because all the registers have 0 in them by default. My bug. But here I am changing my code up here, and it's having an effect. I don't actually have to change any of this stuff I've written down here to get different behavior out of my program. The emulator part, that's handling arbitrary programs at this point. Now, this language can't do everything. Clearly, I mean, there's no equivalent to if statements or looping constructs or anything like that, conditionals. So this language is pretty limited currently. Limited to being able to print Beej, save values and variables and print them out. That's it. But as we push this over the course of the week, we're going to add more and more functionality to it. And by the end of the week, it will be able to do anything. I'm going to share this code with you all, of course. I realize I'm over time, but indulge me for like 2 more minutes. Even functions, yes, even functions. We will be able to do that. We'll get to the equivalent of functions on Thursday. Kind of limited functions, because deep down the CPU is kind of dumb. It only does simple things, but functions nonetheless. So comparing to how this works in a real CPU, the pieces that we've modeled so far are the memory, which are going to exist on as like sticks of RAM on your motherboard, and the registers, which are a different memory space, right? We've got 8 registers that are independent of memory. And those registers are inside your CPU. The registers tend to be really fast because they don't have to go all the way out to RAM. You might think of electricity as being pretty instantaneous, and it is pretty instantaneous, but on a motherboard, RAM's like way over there, a few inches away, and it takes time to go out there and grab that information and bring it back to the CPU. If you can store stuff in registers instead of memory, then great. Registers are faster, but there are a limited number of them. Modern CPU will have 16, 32 registers, and that's it. So those are the 2 pieces of the CPU that we've kind of put together so far. On some CPUs, the memory is on the same chip, like systems on a chip. On most of them, it's not. It's elsewhere on the motherboard because it's bulky. So caches. So are you talking the CPU caching level? Like the cache between CPU and RAM? As opposed to caches inside a program? So if you're writing software that does some kind of caching, the idea with a cache is always, can I take frequently accessed data and make it faster to access? That's always the thing. So even your browser cache, it's answering that question. Can I take frequently accessed data and make it faster? So the browser cache, the slow access is over the network. The fast access is from your hard drive. So it takes stuff over the network, stores copies on your hard drive so it can get them more quickly. So caching at the data structure level is the same thing. And it could be maybe you're loading your data structures off disk and that's slow. So you cache them in RAM because that's fast. And so you take the frequently accessed data structures, put them in RAM, and then you can get them really quickly. But these caching levels happen like all the way through the system. So between the CPU and RAM, there's caching that happens for you automatically. So if you're accessing a lot of data in RAM, the CPU will figure out what you're using frequently, and it'll load that into some super fast memory that sits between RAM and the CPU. And even that memory is split up into multiple levels of caching. So it's more than I want to talk about too much, but the concept is valid, that the cache takes something that's slow to access, looks at what gets frequently used, and makes that stuff fast to access. I don't know, that's rambling. I'm not sure I answered your question there. But and we're totally over time, so everything out from here out is bonus. If you got to split, go ahead and split. I'll post this code. Oh yeah, this is true. So most CPU caches assume that if you've accessed one piece of memory, you're likely to access the addresses right after that. That is the indexes in memory right after that. So if I access a byte that's at index 100, the cache is like, oh, if you got that one, you're probably going to get 101 next, probably 102 and 103 and 104. So it'll go out and it'll grab like 4 kilobytes or something out of RAM all at once. Like, hey, give me all that stuff because I know the user is about to ask for it all. Probably. Maybe it's wrong and it wasted its time, but it's often right. So yeah, if you have your arrays stored contiguously, you can take advantage of caches. I have a demo program I wrote in C somewhere. I can try to dig out where it's a two-dimensional array. If you go across columns first and then down to rows, like you're reading, it's fast. And if you go vertically down the columns first, then it's really slow because it's breaking the cache's assumptions. Oh, is the optimization implemented via registers? So one optimization that happens there, yes, registers are used that way. And if we look at how a compiler builds assembly language for you, like a C compiler, it will use registers as much as it can because it knows they're faster. And so the compiler juggles like which registers it's using for what values. And then it goes to RAM if it has to, because there are only so many registers. Sometimes you have to store them in RAM to have enough space to do all your computation. And it's a bummer when you have to do it because RAM is slow, but the compiler will try its absolute best to keep as much stuff in registers as possible just to keep things going quickly. It'll be like an order of magnitude difference or more, the amount of time it takes to get a value out of memory versus getting it out of a register. Registers are effectively instant. Cool. Good questions. I'll probably show this again later in the week. I don't know how many people have bailed, but there's a website that's useful for breaking this stuff down. This is totally optional. not related to what you have to do this week, except as an interest. Godbolt.org will take C code and it will turn it into assembly code for an x86. So this is for a real CPU, probably the CPU you're running right now. But this is C code on the left. This returns the square of a number. And then this is the assembly code on the right. So we see a bunch of instructions like move and multiply and pop, which is stack oriented. We'll learn all about this stuff later in the week. Whoops, that's not the right bar to drag. There we go. These instructions are different than the LS8 instructions. Each CPU tends to have different instructions, even though they have the same ideas, like registers and so on. So on this CPU, the registers are called things like RBP, RSP, EDI, EAX. These are all registers on an x86. And these are the instructions. And then this numeric value is the numeric value for the instruction. Remember that I said the CPU only knows numbers? These numbers right here represent these instructions. So 89F8, that's move EAX EDI. And 0FAF70FC, that's the multiply instruction by that stuff. So what we're doing is kind of weird in that we haven't written programs like this before, but it actually mirrors reality on a real CPU. We'll look more at that later. Oh yeah, when you're writing assembly, you're writing for that CPU. If you wanted to port it to a different CPU, you'd write some completely different assembly. Which is why C is so nice, because you can write the C once and then build it for different architectures. Let's see, Preston's question. With today's work, what files are you supposed to be working in? That is part of the assignment, to figure that out. So if you get stuck on that, definitely ask a TL. But part of the assignment this week is to go through the stuff and figure out what it is you need to work on. And as a starting point, I recommend the readmes in the main directory and the readme in the LS8 directory, especially that second one, because that one, the readme in the LS8 directory, has a lot more detail. But you might not normally have somebody tell you that. So your first step really should be to go through those subdirectories, everything that's there. Just go through it all at a very high level and write down like what you think this stuff is. Like, how is this useful? And if you don't know, just leave it blank for now, and maybe it'll come together later. But being able to take a big pile of stuff like this and turn it into code is a skill, and that is one of the skills we are explicitly practicing this week. So if you do get stuck, definitely reach out. But in the meantime, start in the readmes in the main directory and in the LS8 directory. And I would expect everybody to spend 1 to 2 hours looking at stuff to figure out the lay of the land. All right, any last questions? Thank you for indulging me for 15 minutes here. Preston, it's gonna seem like a wall of information, like an impenetrable wall. But just pull away at the edges of it and follow those lines of stuff that you don't understand. Like, look for stuff that you don't understand and go out and figure out what that stuff is and move on to the next thing. And just systematically tear down the wall, and pretty soon you'll be there. Let's see, is this code working? Yes, all right. I'll share that all with you. Excellent. All right, gang, keep the questions coming. I'll be hanging out in the help channel when I can, and all the TLs will be as well. And have fun hacking on this stuff. You're gonna write something this week that not a lot of software developers have written. Kind of neat. Most people don't go so far as writing the emulator in their careers, and I think it's unfortunate because they don't realize how easy it actually is. Now I say that, but there are going to be bugs galore that are just going to make you want to rip your hair out. But when it gets done, you're like, okay, there's not actually much to this thing. Go get the next instruction, do that thing. Go get the next instruction, do that thing. That's it. All right, catch you all later, gang. Have a good lunch.